All right, let's dive in. Today, we're talking about one of the most fundamental battles in all of technology. It's this constant tug of war that happens behind the scenes, and it dictates pretty much everything. How fast your games run, how smoothly your videos stream, you name it.
You know, every time you tap an app or load up a website, a core decision has already been made for you. It's a choice that engineers have to make, and it shapes every single interaction you have online, whether you realize it or not. And what is that choice? Well, it really just boils down to this. Should a system be designed to be incredibly fast for just one person's request, or should it be a powerhouse, built to handle a massive number of requests from everyone, all at once? Is it about speed, or is it about scale?
To really get our heads around this, we're going to borrow a fantastic and, a slightly weird analogy from a blog by Dan Sliman. So just imagine, there's a service that takes a picture of a dog, and through some AI magic, it sends back a picture of that same dog wearing a silly hat. Stick with me here. I promise this is going to make perfect sense.
Okay, so this simple, quirky dog hatting service has two very, very different kinds of customers. In their needs, they're completely at odds with each other.
So on one hand, you've got the on-the-spot user. They just took an awesome picture of their dog, and they need that photo like right now for their social media story. They only care about one thing. How fast can I get my one picture back? Then, on the other side, you have the bulk user. This person's a researcher, and they have 1,000 dog photos to process for a project. They don't really care how long any single photo takes. They just want to get through their entire batch as fast as humanly possible.
So these two very different customers, they perfectly represent the two competing goals in any system's performance. So let's go ahead and put some official tech speak on these ideas.
That need for speed from our on-the-spot user? We call that latency. Latency is just a fancy word for delay. It's how long you have to wait for one single thing to happen. The PatSnap blog has a great way to think about it. Imagine latency as the time it takes for one car to drive from the start of a highway to the end. Lower latency just means a faster trip. Simple as that.
And what about our researcher with all those photos? Well, their need for raw processing power is called throughput. This isn't about the speed of one thing, it's about the total amount of work a system can chew through over a period of time. Sticking with that highway analogy, throughput is how many cars can pass a single point on the road every hour. It's all about total capacity.
So let's break this down. Latency is the sprinter. Its goal is to be fast, and we measure it in tiny fractions of a second. For a sprinter to be fast, what does it need? An open track, an empty queue. Throughput, on the other hand, is the marathon runner. Its goal is to be powerful and handle a huge load over time. We measure it in requests per second. And for the marathon runner to be efficient, it wants that queue to always be full so it never wastes a second waiting for more work.
And right there, that's it. An empty queue versus a full queue. That's the fundamental conflict. You just can't have both at the same time.
And hey, don't just take my word for it. This is a huge deal for the folks who actually build these systems. The engineers at Google put it perfectly in their book on site reliability engineering. Low latency users want empty queues, and high throughput users want queues that are never empty. They are fundamentally opposed.
Which, brings us to a kind of impossible question. How can you possibly design a system where the waiting line for service is supposed to be empty and full at the exact same time? The simple, honest answer is you can't. You have to pick one to prioritize.
Okay, so this isn't just some abstract problem for engineers to worry about. This trade-off has huge, real-world consequences in the technology you and I use every single day.
Think about online gaming. Low latency is everything. A millisecond of lag, game over. It's the same for high-frequency stock trading, where a tiny delay can literally cost millions of dollars. But then you flip over to something like video streaming on Netflix or YouTube. Suddenly, high throughput is the absolute king. They need to push a massive amount of data to millions of people to stop that dreaded buffering wheel. The same goes for big data or running giant reports overnight.
So here's the bottom line. You can't build a system designed for a single lightning-fast race car and then expect it to work like a 10-lane superhighway with tons of traffic. It just doesn't work that way. Engineers have to make a choice. So if you can't have it all, how do engineers actually deal with this? Well, this is where it gets really interesting, where system design becomes less of a rigid science and, honestly, more of an art. Engineers have this whole toolbox of tricks they can use. They can set up a fast lane for the really urgent data. They can use something called caching, which just means storing popular stuff closer to you so it's faster to get. They can even split the work entirely, build one system for speed and a totally separate one for volume. Even the basic protocols they choose for the internet, like TCP or UDP, are a trade-off between guaranteeing something arrives and just sending it as fast as possible. But here's the kicker. Even with all these clever strategies, things get, well, they get messy. How do you actually prove that one system is really, truly better than another? Okay, check this out. This is a classic trap, based on some lecture notes from Sapienza University. You've got two systems, A and B. System A is twice as fast as B on the first job, but System B is twice as fast as A on the second job. So, which one is actually better? Seems simple enough, right?
Well, let's say you're analyst A. You decide to measure everything relative to System B. So, System A is 2 times faster here and half as fast there. Average those two out, and boom, your conclusion is clear. System A is 25% better. Case closed. Or is it?
Because what happens if analyst B comes along, looks at the exact same data, but decides to measure everything relative to System A instead? Well, now System B is half as fast on the first job, but 2 times faster on the second. The math flips completely. All of a sudden, System B is the clear winner, also by 25%.
This is just brilliant, right? You have the same raw data leading to two totally opposite conclusions, and both are technically correct. This whole ratio game, as it's called, shows that you can't just blindly look at the numbers. Evaluating performance is a subtle art. It really is.
To cut through this kind of confusion, engineers lean on fundamental rules, and one of the biggest is called Little's Law. All you need to know is that it's a powerful formula that shows a direct mathematical link between the number of things in a queue, how fast new things are arriving, and how long each one takes. It's basically the mathematical proof behind this entire trade-off we've been talking about.
So the next time your favorite app feels a little sluggish, or your game lags, or a video has to buffer, now you know why. A choice was made deep in its code. So ask yourself the question, was this thing I'm using built to be a sprinter or a marathon runner? Was it designed for my immediate speed or for everyone's massive scale? The answer to that question is at the very heart of how our digital world actually works.